Hello and welcome to Honors Function. Again, in this lecture, we are continuing our exploration of algebraic tools that allow us to look for the roots of polynomial. In this lecture, I will introduce two important tools, the rational root theorem and the conjugate root theorem. Let's start with the rational root theorem. So let's take a polynomial p with degree n. So I'm going to assume that the degree of p is n, and that means that an is not 0. Okay? Let's assume that this polynomial has a rational root. Rational root, so p over q, right? Let's assume that there is a p and q integers such that p over q is a root of the polynomial. Now you know the equivalence between a root and, it's an equivalence, and a factor, right? So it's going to be qx minus p, which is going to be a factor. Factor and root of p, of course, all right? So I can write p of x as qx minus p times, and here I will have a quotient polynomial, right? Now the degree of p is n, right? The degree of p is n. So this quotient polynomial must have a degree of, well, n minus 1, right? Okay, so let's take a polynomial of degree n minus 1. So I have p of x equals qx minus p, and here I'm going to take standard form of a polynomial of degree n minus 1. So it's going to be b n minus 1 x n minus 1 plus b1 x plus b naught. Okay, now if you expand this, and I'm not going to expand the whole thing, but if you expand this, what's going to be your leading term? It's going to be this right here, right? So it's going to be q times bn minus 1 times xn, all right? Plus a lot of terms in the middle, but the last term will be what? It's going to be, I guess, a minus, I should say, okay? So minus p b naught, right? If you expand it all, that's what you find. But p of x, we assumed it was an xn plus a1x plus a naught. So what do you have here? You have an equality of two polynomial. Of course, they have the same degree or they couldn't be equal. And two polynomials are equal if and only if the corresponding coefficient are equal. So an has to be equal to q times bn minus 1, and all of them until the last one, a naught, has to be equal to this right here. So let's write these two equality. We have an equals q times bn minus 1, and we have a naught equals negative p times b naught. Okay? So remember we started with p and q. Now p appears as a factor. P is a factor of a naught, and q is a factor of an, right? I mean, it's written right here. If you write an equals q times bn minus 1, then q divides an. Q is a factor of an. Same thing with p. So what do we have now? If p over q, again, p over q, if it's a big if, okay, we don't know if we have a rational root. If p over q is a root of p of x, okay, then what? Then p divides the constant term, and q divides the leading term. And this theorem sometimes allows us to find roots of polynomial. It may be a bit long to use. You have to use, this is called the rational root theorem. These are my contractions, okay? We don't say that in math, it's just faster. And I use that in conjunction with the intermediate value theorem. Actually, it's a corollary of it, a change of sign in the output, indicates a 0 in the input. That's a corollary, but I just call it IVT, intermediate value theorem, and RRT. Let me show you on the first example how these two theorems will allow you to sometimes find roots of polynomials. Let's start with example 1. Now look at that. You have to solve a degree 4 equation. This is not easy in general. This is not easy in general, okay? So my first approach is to get a couple of output, and I will keep track of IVT, intermediate value theorem. If I have a sign change in the output, I'm gonna think maybe there is a 0 that I can find in the input. I mean, I know there will be a 0, but maybe I can find it if it is rational. Let's see how that works. So of course, I always start with f0. f0 is negative 18, therefore it's negative. What is f of 1? f of 1, well, it's easy, right? All x's are 1, so it's 4 plus 20 minus 3 minus 42 minus 18. You do not need to do a synthetic substitution for f of 1. It's right there. Now, f of 1, if you look at it quickly, again, that's going to be negative. Okay, now, look. The way I explore my roots, I start with 0, I go to 1. If I haven't found a sign change in the output, my next one is negative 1. Why? Because these are easy. If I don't find a sign change in the output between 0 and negative 1, I will go to 2. And then I will go to negative 2. Unless I have a reason to not move in a direction. Let me show you what I mean by that. Suppose all the terms right here are positive, right? Suppose all the terms are positive, and if f of 0 is positive, okay, and all the terms are positive, then when you plug 1 for x, or 2, or 3, or 4, you will not find any roots. It's just gonna increase and increase and increase. So there wouldn't be any reason for you to move in the positive direction. So you always have to pay attention to the coefficient. This is not quick work, okay? This is not quick work. All right, let's check out f of negative 1. f of negative 1, so I'm going to keep my even degree, right? And I'm not going to change my coefficient, and all the odd degree will change to a negative. So I have plus 4 minus 20 minus 3 plus 42, okay? 42 times negative 1 is negative 42, and you have a negative sign inside, minus 18. Now let's take a quick look at this. I have negative 20 and negative 18, negative 38. Negative 38 and negative 3 is negative 41. Okay, that is positive. Uh-oh, there is a root between. Look, f of 0 was negative, right? F of 0 is negative, and f of negative 1 is positive. There is a root between 0 and 1. Okay, now it's time to look for the possible rational root. If this root is rational, if it is rational, I'm going to find it because I know all the possible rational roots. So let's see. If p over q is a root of f of x, then what? Then p divides, the top divides the last, p divides negative 18, and q, this is how I write divides, okay? And q divides 4. Well, I know all the divisors of negative 18. P equals plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, 5, 6, plus or minus 7, 8, 9, plus or minus 18. That's it. Q equals plus or minus 1, plus or minus 2, plus or minus 4. All right, so now let's write all the possible rational roots, okay? So I will take P and I will put it over Q. I do it like this. Sometimes students do it differently, okay? This is the order I take. So I have plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. Okay, I'm done with all the ones. So now I will do the same with 2. Okay, and don't repeat a root, okay? So you have plus or minus 2, 2 over 2, that's 1, 2 over 4, that's 1/2. I got it. All right, now let's do the same with 3. So we have plus or minus 3. 3 over 2, I don't have it. 3 over 4, I don't have it. All right, next one. Plus or minus 6. Plus or minus 6 over 2, that's 3. 6 over 4, 3/2, I got it. Plus or minus 9. 9/2, I don't have it. 9/2. Plus or minus, I'm going to go here, 9/4. Then plus or minus 18. and 18 over 2 and 18 over 4, I have them. Wow, that's a lot. Check it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and because of the plus or minus, 24 possible rational roots. Okay, rational roots. 24 possible rational roots. That's a lot to check, okay? But fortunately, we're using IVT. So look what I said here. There is a root between 0 and -1. All right, so between 0 and -1, what do I have? I have -1/2 and -1/4. And that's it, right? -3/2 is not, okay. So I'm going to check -1/2 and -1/4. I will start with -1/2. Again, guys, this is not the quickest kind of work. All right, so you have 4, 20. I'm doing a synthetic substitution, right? -3, -42, and -18. Okay, let's do that quickly. We have 4, -2, 18, -9, -12, 6, 36, -36, 18. Oh, yes, nice, I have it. All right, so we got a root, -1/2. Now, we need to find one more, right? We have a degree 4. If I have a root, this one is a degree 3. I need to find one more root. Okay, let's see where we were. We checked 0, we checked 1, we checked -1. We did find a root right here. So the next number I'm going to check is 2. I want to check 2 and see if there is a sign change between 1 and 2. F of 1 was negative. Let's see what f of 2 is. So 2, what do we have? A 2. We have, so 4, 20, -3, -42, and -18. Okay, let's go. So 4, 8, 28, 56, 53, 106. Okay, I'm going to stop here because look, this is going to be a positive number pretty big in the 60s, somewhere in the 60s. And I'm going to multiply by 2. I'm going to be somewhere in the 120s. So this is positive. So f of 2 is positive. F of 2 is positive. So there is a root between 1 and 2. There is a root between 1 and 2. If it is a rational root, if this root is in Q, it's a big if, okay? If this root is in Q, I'm going to find it because now I have all my possible rational roots. So which one is in between 1 and 2? 3/2 right here. And that's it, right? 3/4 is not. 9/4 is not. Okay, so that's the only one. So if it is rational, it's going to be 3/2. If 3/2 doesn't work, then it's not rational. Okay, look, I'm running out of space here, so I'm going to erase this right here, and I'm going to do the same thing with 3/2. Okay, so let's check out 3/2. Okay, divide by 2, multiply by 3. Divide by 2, 2 times 3, 6. 26. Divide by 2, 13 times 3, 39. 36. Divide by 2, 18 times 3, 54. 54 and -42, 12. Divide by 2, 6 times 3, 18. I got it. Okay, I got it. So, hey, we have two roots now. Let's continue. We know that 1/2 or -1/2 is a root, right? So let's continue. So 4, -2, 24, -12, 24, -12, 0. All right. Now, be careful here. You are not allowed to change the factor, okay? You have, did I call it f? Yes. You have f of x equals, so x minus 3/2. Don't write it as 2x minus 3. You are not allowed to change the factor because you're doing a synthetic division. This is the quotient you are finding, okay? If you change the factor, you know the coefficient of the quotient will be different. X minus 3/2, that's a 0, so that's a factor. X plus 1/2, and then where's my quotient? 4x squared plus 24x plus 24. Now, this is what's going to happen, right? Check it out. I am going to take a 4 out of that. I'm going to take 4 out of that, right? I can take a 4. 4 is 2 times 2, right? I'm going to give 1, 2 to this factor, and I'm going to give the other one to this factor. So what do we have? We have, if you multiply this by 2, you get 2x minus 3. Here it is, okay? You find it, but you cannot cheat with the coefficient here. Then you have 2x plus 1. Then if you take a 4 out, what do you have? You have x squared plus 6x plus 6, right? And this is what you have to factor. Let me see what we want to do. We want to solve the equation. Okay, we want to solve the equation. So therefore, I need to make this equal to 0. X squared plus 6x plus 6 equal to 0. Complete the square. X plus 3 squared minus 9 plus 6, that's minus 3, so equals 3. And so you would have x equals negative 3 plus or minus root 3. So the zeros are, we have 3 half, negative 1 half, negative 3 plus or minus root 3. Okay, these are my zeros. And if you were to factor the polynomial, how would it factor? So f of x is, sometimes you need to write the factorization, 2x minus 3, 2x plus 1, and then what? And then you have two roots there, right? You got negative 3 plus root 3, and then you got negative 3 minus root 3. And each root leads to a factor, x minus that, and then x minus this, right here, right? So we have two more factor. We got x, so distribute the negative sign here, right? X plus 3 minus root 3, and x plus 3 plus root 3. This is a factorization of f. You always have to check that the leading coefficients in f and in your factorization do match. The leading coefficient of f is 4, right? Lead coef is 4. And the leading coefficient here is, it is 4 too, okay? Because there's 1 and 1 right here. It is 4. So yes, they match. Therefore, I have the right factorization. Sometimes, when you go from the 0 to the factorization, you may mess up the leading coefficient. So just check at the end that they match. So hey guys, this is not the shortest kind of work, but it is very, very important. I hope you understand now how to use IVT, or the corollary of IVT, in conjunction with the rational root theorem. Okay, so this is the first big theorem of this set of notes. If the polynomial has a rational root, there is a way for you to find it. Now let's look at another application of this theorem. It's kind of interesting, proving that a number is not a rational number. Check it out. I'm going to show you that the root 2 is not irrational. So look, I'm going to look at the polynomial f of x equals x squared minus 2, right? X squared minus 2. What are the roots of x squared minus 2? F of x equals 0 if and only if x is plus or minus root 2, okay? So how do you know that this is not in Q? How do you know that? Well, if this polynomial has any rational root, right, p over q, p divides 2, q divides 1, so p over q equals plus or minus 1 or plus or minus 2, okay? When q is only plus or minus 1. So this is super easy. You take all the factors of the last. So plus or minus 1, plus or minus 2. This would be the only rational root. If this polynomial has any rational root, it's going to be plus or minus 1 and plus or minus 2. Now you can check that these two values will not make the polynomial equal to 0. Okay, if you do f of plus or minus 1, this is not 0, and f of plus or minus 2, this is not 0. Therefore, this polynomial doesn't have any rational root. Therefore, plus or minus root 2, which is a number that I don't know at first, okay, but I can tell you right now, it is not rational. Okay, so it's kind of an interesting application of the rational root theorem. Let's now move on to the second big theorem of this section. Please make sure you do example 2 and 4. Example 2 is just a cubic. I have taken the longest example, example 1, which is a quartic equation, okay? Example 2 should be faster. All right, let's move on to the complex root theorem or conjugate root theorem. So hey, I am not going to prove this one. It is really not difficult to prove it, but I'm not going to prove it. Basically, the conjugate root theorem is telling you that if f of x has real coefficient only, okay, real coefficient, so it doesn't work with complex coefficient, but if it has real coefficient only, and if z in C is a root, okay, if f of z is equal to 0, then, this is how I write if then, right? Then f of the conjugate of z, z bar, is also equal to 0. So basically, it says that if your polynomial has real coefficient only, complex roots come in pairs, okay? They always come by twos. There is an hypothesis of the first theorem that I didn't mention, and maybe we need to mention it. So let's quickly look at the first theorem. See right here, I didn't mention this hypothesis. You need your polynomial to have integer coefficient only, right? Integral coefficient. It wouldn't be true, this theorem is not true if the polynomial has real coefficient. For example, some root 2 x cubed plus, okay, that wouldn't work. But it's kind of obvious that it wouldn't work, all right? So that's why I didn't mention it, but it's kind of an important hypothesis. So let's move back now. Sorry about this little parenthesis. Let's move back to the conjugate root theorem. So I call this theorem CRT, conjugate root theorem. Let me show you how it applies. All right. So I am asking you to do a synthetic substitution with this polynomial to show that actually, let me see. Oh, we're probably going to find that this is a root, okay? So how do you do a synthetic substitution? Well, that's easy. You write the value right here and you just do it in the regular way. So leave a little bit more space here because you're going to write complex number 3, negative 4, 11, and 10. Okay, here we go. All right, bring down the 3, multiply by 1 plus 2i. So this is 3 plus 6i. 3 plus 6i minus 4, only the real part will add. This is negative 1 plus 6i. And then right here, we have to multiply by 1 plus 2i. Now, I know how to do that, but it's kind of a pain. Therefore, all this work right here, all this work, do it in your calculator. You will see it's super nice and super easy. Let me take the calculator. The first thing I'm going to do with my calculator is store the complex number given to me. So 1 plus 2, I is right here, blue right there on top of the, okay, here we go. And I'm going to store that, for example, in A. So alpha A, right here. Okay. I've stored my complex number in A. And now look what I have to do, okay? I have to, this is A right here. So I have to do 3 times A. All right, let's do 3 times A. So times 3 equals, and then what? And then you have to add negative 4. So minus 4 equals, well, we had this, okay? This is what we had right here. But now what? Now I need to multiply by A. So that's what I'm going to do. Times alpha A. It's going to make your computation so quick. This is negative 13 plus 4i. So here you write negative 13 plus 4i. Now, I could do that by hand easily, right? Negative 2 plus 4i. But because I'm using my calculator, I have to keep track of it. So what am I adding now? I'm adding 11 plus 11 equals, and now let's go back up, times A, alpha A, and this is negative 10. All right. Oh, beautiful. That's a root. All right. This is a root. So if it's a root, I'm going to extend my synthetic because I know that 1 minus 2i is also a root. I know that because my polynomial has only real coefficient, right? Okay, let's do another synthetic. For this one, you don't need the calculator because it's gonna be very simple. You'll see everything will be real here. So bring down the 3 times 1 minus 2i. So this is 3 minus 6i, right? And this is just 2. All the I will cancel. Times 1 minus 2i. This is 2 minus 4i. And this is 0. Got it. Alright, that was a degree 3, therefore this is a degree 2, and this is a degree 1. I am done. Okay, f of x is equal to x minus 1 minus 2y times x minus 1 plus 2y times 3x plus 2. So I got all my roots. I'm not going to write the roots because the video is a little bit on the long side. I'm going to stop right here. But if you got the factorization, of course, you got the root. Thank you for watching.